Dear cadets, Assalamu alaikum. Welcome you all at my online class. I hope all of you are well by the grace of Almighty Allah. This is Maksud Rahman, lecturer in chemistry, Borishal Cadet College, Borishal. It is very necessary to keep yourself inside home along with your family members for avoiding the running pandemic COVID-19. I hope that we will very soon can get rid of from this pandemic condition and once again our life become a smooth one. Considering this prevailing situation, Borishal Cadet College is providing necessary academic guidelines and short lecture on space link periodically. With this continuation, I am here for your online class. Okay, boys, what you can see? Yes, in this picture, you can see about the Arrhenius equation. This is the Arrhenius equation, and here we can see the effect of catalyst. Yes, today I am going to discuss on chapter 4 chemical change, and this is my second session, and today we basically discuss on Arrhenius equation and catalyst. At the end of this lesson, you will be able to describe Arrhenius equation, solve exercise based on Arrhenius equation. You can define catalyst. You can also explain different types of catalyst. You can analyze the mechanism of homogeneous and heterogeneous catalyst. First one, rate of reaction. In my previous lecture, I discussed on rate of reaction. For your better understanding, I repeat it here. You already know that rate of reaction means the speed of the reaction. How does a reaction, how fast a reaction occur? For example, wood conversion has a high reaction rate since the process is very fast, and the rusting of iron has a low reaction rate as this process is a slow process. So in this picture, rusting is a slow process, so its rate of reaction is very slow. For rusting, it takes many times, so rusting is a slow process. Baking, we know that baking is not very slow, it is a little bit faster than rusting, and in case of explosion it is very fast, so its rate of reaction is also very high. So we can say that different reactions have different rate of reaction. Some reactions occur slowly, some reactions occur little bit faster, and some reactions occur very fast, like explosion. So Arrhenius equation. The Arrhenius equation is an expression that provides a relationship between the rate constant, the absolute temperature, and a factor. What is a factor? A is known as pre-exponential factor. It provides insight into the dependence of reaction rates on the absolute temperature. That means Arrhenius equation basically provides a relationship between the rate of reaction with the absolute temperature. That means temperature. If temperature increases, how the rate of reaction changes, it will discuss in Arrhenius equation. The general expression of Arrhenius equation is K equal to A e to the power minus A divided by RT. So what is K or E or EA or R or T? Where K denotes the rate constant of a reaction. So K is rate constant. What is A? A denotes the P exponential factor, which in terms of collision theory, it is a frequency of correctly orientated collisions between the reacting species. What is E? E is the base of the natural logarithm, you know it. And EA already I discussed in my previous lecture. EA is equal to activation energy of a chemical reaction. R is denotes the universal gas constant or molar gas constant, and T equal to absolute temperature associated with the reaction, and must be, when you calculate any mathematical problem, you must convert this T into in Kelvin scale. So if the activation energy is expressed in terms of energy per reactant molecule, the universal gas constant must be replaced with the Boltzmann constant in the Arrhenius equation. The Arrhenius equation was forward by the Swedish chemist Svante Arrhenius in the year of 1889. So you can understand what is Arrhenius equation. Arrhenius equation basically expresses the relationship between the reaction rate and temperature, and its equation is K equal to e to the power minus Ca divided by RT. Here K is equal to rate constant, K is equal to Arrhenius constant, or you can say pre-exponential factor of in terms of collision theory. E equal to activation energy, R equal to molar gas constant or universal gas constant, and T equal to absolute temperature, and it must be expressed in Kelvin scale. Okay boys, considering a chemical reaction at two different temperatures. So if you have two different temperature, what will be the expression of Arrhenius equation? Considering temperature T1 and T2, and whose corresponding rates constant are K1 and K2 respectively. So we can write ln K1 equal to ln A minus A divided by R T1, and ln K2 equal to ln A minus A divided by R T2. The second equation can be rearranged to get the value of ln A. So ln A equal to ln K2 plus A divided by RT2. So substituting this value of ln A in the first equation ln K1, the following equation can be obtained: ln K1 equal to ln K2 plus A divided by RT2 minus A divided by RT1. So shifting ln K2 to the left hand side, the value ln K1 minus ln K2 becomes A divided by RT2 minus A divided by RT1. The left hand side of this equation in the form ln x minus ln y. So we can write simply ln x by y, and also in term E divided by R, you can see that E divided by R is a common factor in the both terms in the right hand side. So we can write it ln K1 divided by K2 equal to minus A divided by RT, A divided by R bracket 1 by T1 minus 1 by T2. So this is the equation for if two different temperature is present, two different temperature. This is the general expression of Arrhenius equation. Now a mathematical problem. The activation energy of a chemical reaction is 100 kilojoule per mole, and its a factor is A m minus S m to the power minus 1 S to the power minus 1. Find the rate constant of this equation at a temperature of 30 Kelvin. So here you can see here values are activation energy, that means EA, A factor, that means A, and T, and given temperature is 300 Kelvin. So given that activation energy equal to 100 kilojoule per mole, so A equal to 10 per m per second, ln A equal to 2.3 approximately, so and T equal to 300 Kelvin. So the value of the rate constant can be obtained from the logarithm form of the Arrhenius equation. You already know the Arrhenius equation, ln K equal to ln A minus E A divided by RT. Putting this value, you can find out the value of K. K equal to 3.8341 into 10 to the power minus 17 per m per s. From the units of the A factor, it can be understood that the reaction is a second order reaction, and for which the unit of K equal to per m per s. Therefore, the value of the rate constant for the reaction at a temperature of 300 Kelvin is approximately 3.8341 into 10 to the power minus 17 per m per s. So you can solve this problem. Solve if this problem are like this. Here is another problem. At a temperature of 600 Kelvin, the rate constant of a chemical reaction is 2.75 into 10 to the power minus 8 per m per sec per s. When the temperature is increased to 800 Kelvin, the rate constant for the same reaction is 1.95 into 10 to the power minus 7 per m per s. So here you can see there are two different temperature. For two different temperature, there are two different rate of reaction. So I think you can understand what equation you can now apply. Question is, what is the activation energy of this reaction? At first, I say that you first write down what are the values are given. Here T1 equal to 600 Kelvin and K1 equal to 2.75 into 10 to the minus 8, T2 equal to 800 Kelvin and K2 equal to 1.95 into 10 to the minus 7. So when the A factor is eliminated from the Arrhenius equation, the following equation is obtained. You already know that ln K1 by K2 equal to minus A divided by R, 1 by T1 minus 1 by T2. Now putting this value, you can find out the value of EA. EA equal to 39716 joule per mole. So you can find out the activation energy of this reaction is approximately 39716 joule per mole. Using what is the use of Arrhenius equation? I in my previous slide I said that Arrhenius equation basically express the relationship between reaction rate and temperature. So when we can change the temperature, what will be the effect on the rate of the reaction? It will be expressed by Arrhenius equation. For example, what happens if you increase the temperature by 10 degrees Celsius, say 20 degrees Celsius to 30 degrees Celsius? The frequency factor A in the equation is approximately constant for such a small temperature change. So we need to look at how e to the power minus A divided by RT changes. So if this changes for changing of temperature, we can find out the relationship between rate constant and temperature. Here at 20 degrees Celsius temperature, in Kelvin scale, its value is 293 Kelvin. This e to the power minus A divided by RT fraction is, we can find out the value 1.21 into 10 to the power minus 9. So now, if we increase the temperature to 30 degrees Celsius temperature, that means 303 Kelvin. What will be the change in e to the power minus A divided by RT? Here you can find out the value of e to the power minus A divided by RT equal to 2.38 into 10 to the power minus 9. So it is totally double of this previous one. So we can see that the fraction of the molecule able to react has almost double. This value is double of this value. So we can say that if we increase temperature by 10 degrees Celsius temperature, only 10 degrees Celsius temperature, the reaction rate will be double. So we can say that if the temperature of a reaction is increased by 10 degrees Celsius temperature, the reaction rate increased double. So this is very important question for you. I think if you have any question, so for example, what happens if you increase the temperature by 10 degrees Celsius temperature, 10 degrees Celsius, how the rate of reaction changes? So I think you can solve this problem and you can write down the answer of this question nicely. Now I am going to discuss on catalyst. So what are catalysts? In chemistry, catalysts are defined as those substances which alter the rate of reaction, by changing the path of the reaction. Most of the time, catalyst is used to speed up or increase the rate of reaction. However, if we go into a more deeper level, catalysts are used to break or rebuild a chemical bonds between the atoms which are present in the molecules of different elements or compounds. In essence, catalysts encourage molecules to react and make the whole reaction process easier and efficient. So in a short, if we can say catalysts are those substances which can increase or decrease the rate of reaction, but it does not initiate the reaction or ends up a reaction. It only accelerates or retards a chemical reaction, and it never takes place in the reaction, and after the reaction the total amount of catalyst will be remain same. Some of the important characteristics feature of the catalyst are: a catalyst does not initiate a chemical reaction. A catalyst does not initiate a chemical reaction. A catalyst does not consume in the reaction. So after the completion of the reaction, the total amount of catalyst will be remain same. So a catalyst does not consume in the reaction, and a catalyst needed in small in amount, not much catalyst are used in a specific reaction. Only a few amount of catalyst is needed, specific for a particular chemical reaction. That means for a specific reaction, a specific catalyst is needed. Catalysts tend to react with reactants to form intermediates and at the same time facilitate the production of the final reaction product. After the whole process, a catalyst is regenerated. So total amount of catalyst ultimately, total amount of catalyst will be remain same at the initial and at the final. A catalyst can be either solid, liquid or gaseous catalyst. So some of the solid catalysts include metal or their oxides, including sulfides, halides, semi-metallic elements such as boron, aluminum, silicon also used as catalyst. Liquid and gaseous elements which are in pure form are used as catalyst. Sometimes these elements are also used along with suitable solvent or carriers. The reaction which involves a catalyst in their system are known as catalytic reaction. Now, types of catalyst. There are several types of catalysts that can be depending on the need or requirement for a chemical reaction. They are as follows. First one is positive catalyst. Second one is negative catalyst. What is positive catalyst? Catalysts which increase the rate of reaction are known as positive catalyst. Here you can see activation energy for the catalyst that are when we don't use any catalyst. But if we use catalyst, here you can see this is the activation energy. This activation energy much higher when we don't use any catalyst. But if we use catalyst, this activation energy becomes lower. So this activation energy becomes lower. That's why reactions now easily reactants now easily converted into product as activation energy is low. So catalysts which increase the rate of reaction are positive catalyst. It increases the rate of reaction by lowering the activation energy. You can see in this picture, it increases the rate of reaction by lowering the activation energy barriers such that a large number of reactant molecules are converted into products. Thereby the percentage of yield of products increases. So positive catalysts basically lower the activation energy, so much amount of reactants converted into products, so rate of reaction increases. For example, in Haber-Bosch process during the production of ammonia gas, we use iron oxide as positive catalyst, and it increases the yield of ammonia in spite of less reaction of nitrogen. Now, negative catalyst. Catalyst which decrease the rate of reaction is called negative catalyst. How it decreases? It increases the activation energy, so less amount of reactants converted into product. So negative catalyst basically increases the activation energy. It does not lower the activation energy. It increases the activation energy. Example is decomposition of hydrogen peroxide into water and oxygen is retarded by using acetanilide. So if we use acetanilide in the decomposition reaction of hydrogen peroxide, it retards the reaction. So this acts as a negative catalyst to decrease the rate of decomposition of hydrogen peroxide. Now, induced catalyst. What is induced catalyst? When one reaction influences the rate of another reaction, it does not participate in reaction. It does not a catalyst. When one reaction influences the other reaction, influences the rate of other reaction, which does not occur under ordinary condition, the phenomenon is called induced catalyst. I repeat it. When one reaction influences the other reaction, that means this reaction does not occur under normal condition, but due to the influence of this reaction is occurred. That's why this process is called induced catalysis. For example, sodium arsenide solution is not oxidized by air. Let's try to understand. Sodium arsenide solution is not oxidized by air. If, however, air is passed through a mixture of solution of sodium arsenide and sodium sulfide, both of them undergoes simultaneous oxidation. But if you use sodium arsenide only, it does not undergo oxidation. But if we oxidized a mixture of sodium arsenide and sodium sulfide, both can be oxidized. So we can say, due to the presence of sodium sulfide, sodium arsenide undergoes oxidation. So this influences the oxidation of sodium arsenide. So this is induced catalyst. I think you can understand. I repeat it here. Sodium arsenide solution is not oxidized by air. So if air is passed through a mixture of solution of sodium arsenide and sodium sulfate, both of them undergo oxidation. So the oxidation of sodium sulfite, that induces the oxidation of sodium arsenide. So sodium sulfide is induced catalyst. I think it is clear to you. Second one, the reduction of mercury chloride with oxalic acid is very slow. Reduction of mercury chloride with oxalic acid. So reaction of mercury chloride with oxalic acid is very slow. But potassium permanganate is reduced readily with oxalic acid. So mercury chloride and oxalic acid reaction is very slow, but reaction of potassium permanganate and oxalic acid is very fast. So if oxalic acid is added to a mixture of potassium permanganate and mercury chloride both, then the reduction of potassium permanganate, both the reaction reduce simultaneously. That means the reduction of potassium permanganate induces the reduction of mercury chloride. I think it is clear to you. If it is not clear to you, I repeat it here. Mercury chloride react with oxalic acid very slowly, and potassium permanganate react with oxalic acid very fast. So if we use oxalic acid in the mixture of mercury chloride and potassium permanganate, then both the reactions occur faster. So as this was in previously this was in slow process, but due to the presence of potassium permanganate, it is now fast process. So potassium permanganate acts as a induced catalyst. It influences to reduce mercury chloride. So as potassium permanganate induce mercury chloride to reduced, that's why potassium permanganate is induced catalyst, act as a induced catalyst. Now autocatalysis. What is autocatalysis? In the autocatalytic reaction, there is no specific catalyst that is added. Instead, one of the product acts as a catalyst and increases the rate of reaction. For example, decomposition of arsine AsS3 is formed by the arsenic formed in the reactor is autocatalyst. So here you can see decomposition of arsine, we get arsenic and hydrogen. When this arsenic form, this reaction get faster, or the rate of reaction becomes faster. So this arsenic now act as a autocatalyst. Another example, potassium permanganate, reaction of potassium permanganate and oxalic acid during the process of formation of, during this reaction, manganese Mn2 plus form, and Mn2 plus now act as a catalyst for this reaction. So this substance form in this reaction and act as a catalyst. So this is called autocatalyst. When a substance formed during the reaction and act as a catalyst, this substance is called autocatalyst. We does not use this catalyst from outside. This is generated during the chemical reaction and also act as a catalyst. That's why it is called autocatalyst. Another one is catalyst promoter or accelerator. It is not basically a catalyst, but a substance which increases the activity of catalyst. I repeat it again, this is not a catalyst. When a substance increases the activity of the catalyst is called catalyst promoter. For example, in Haber-Bosch process, molybdenum or a mixture of potassium and aluminum oxide act as a promoter, and iron oxide is a catalyst, and molybdenum or mixture of potassium and aluminum oxide act as a catalyst promoter. That means it increases the activity of iron oxide. So that's why it is called catalyst promoter. This is not a catalyst, but it increases the activity of the catalyst. Now, catalyst inhibitors. What is catalyst inhibitors? The substance which decreases the activity of the catalyst are known as the catalyst inhibitors. For example, in the hydrogenation of alkyne to alkene, palladium is poisoned with barium sulfate in quinolone solution. The reaction is stopped at the alkene level. So this catalyst is called Linder catalyst. So as this catalyst decrease the activity of the catalyst, that's why it is called catalyst inhibitors. Basically, during the hydrogenation of alkyne, it first produce alkene, then alkane. But if we use palladium, is poisoned with barium sulfate. If we use palladium catalyst, so alkyne converted into alkane. But if this palladium is poisoned with barium sulfate in quinolone solution, this alkyne now stopped in alkene step, not alkane. That's why barium sulfate and barium sulfate in quinolone solution is act as a catalyst, poison or inhibitors. Now, what is the catalysis? When a catalysis is used to make a reaction, thus when a catalyst is used in a reaction, the process is known as catalysis. On the basis of the nature and physical state of substance employed in a chemical reaction, catalysis is of three types: homogeneous catalysis, heterogeneous catalysis, and autocatalysis. In my previous slide, I discussed about autocatalysis. Now I am going to discuss on homogeneous catalysis and heterogeneous catalysis. First one, heterogeneous catalysis. Heterogeneous means in this type of catalysis, the reacting substance in a reaction, that means reacting substance and the catalyst are not in the same state of the matter. For example, during preparation of ammonia by Haber-Bosch process, we use solid oxide, iron oxide as a catalyst, but hydrogen and nitrogen both are gases. So reacting substance, that means hydrogen and nitrogen are gaseous substance, but we use solid iron oxide as a catalyst. So this is solid state, but reacting substance are gaseous. So that's why it is called heterogeneous catalysis. Another example, manufacture of sulfuric acid by contact process. During the contact process, we use sulfur dioxide converted into sulfur trioxide. So sulfur dioxide, when reacts with oxygen in presence of vanadium pentoxide catalyst, it converts into sulfur trioxide. Sulfur dioxide, oxygen, sulfur trioxide, both are gaseous substance. All are gaseous substance, but vanadium pentoxide is solid substance. So as the catalyst and the reacting substance are in different state, that's why it is called heterogeneous catalysis. Now, what is the mechanism of heterogeneous catalyst? Heterogeneous catalysis involves both adsorption as well as intermediate compound formation. Reactants molecules, at first reactant molecules, you can see in this picture, at first reactant molecules, methane, here you can see ethene and hydrogen. When ethene and hydrogen react in presence of nickel catalyst, it produces ethane. So during this formation of compounds, what is the mechanism of this reaction? So this undergoes heterogeneous catalysis, it follows heterogeneous catalytic mechanism. So at first, the reactant molecules, hydrogen and ethene, adsorb on the nickel catalyst, surface of the nickel catalyst. So this combined to the form an activated complex with an intermediate compound, form an intermediate compound. This compound then decomposes to give products. As soon as the product form, this gets dissolved from the surface without any lapse in time. The heterogeneous catalysis involves initially adsorption. First it forms initially adsorbed on the surface of the catalyst, and intermediate substance is formed, then dissociating into a product, and example is hydrogenation of ethene into ethane in the surface of the nickel catalyst. First one, ether and hydrogen molecule are absorbed on the surface of the catalyst. Ethene and hydrogen molecule are absorbed on the surface of the catalyst. Then ethane molecule attract at its double bond region to form an activated complex, and ether react with active hydrogen to form ethane. This ethane gets dissolved on the surface of the catalyst. Now, homogeneous catalysis. The catalysis in which the catalyst employed in the reaction and the reactants are in the same state or matter, that process is called homogeneous catalysis. For example, hydrolysis of ethyl acetate in the presence of dilute acid. Here ethyl acetate is a liquid which contains an ester functional group. This is the ester functional group. It reacts with water. In the presence of little sulfuric acid or hydrochloric acid, is a liquid to give ethyl alcohol and acetic acid. In the above reaction, reactants and catalyst are in the same state of matter. That's why it is called homogeneous catalysis. Another example, oxidation of sulfur dioxide in the lead chamber process. Lead chamber process is used in the manufacture of sulfuric acid. In this process, nitric oxide gas is used. So here you can see that sulfur dioxide and oxygen react with each other and form sulfur trioxide in presence of nitric oxide. So sulfur dioxide, oxygen, sulfur trioxide and nitric oxide, all these substances are gaseous substances. So as catalyst and reacting substance are gaseous, that means in the same state, so we can say this is a homogeneous catalysis. So what is the mechanism of homogeneous catalysis? The homogeneous catalysis takes place by intermediate compound formator theory. It does not undergo absorption or adsorption. For example, sulfur dioxide when react with oxygen, it forms sulfur trioxide in presence of nitric oxide. So how it form? At first, this catalyst react with oxygen and produce nitrogen dioxide, and this nitrogen dioxide react with sulfur dioxide and it forms sulfur trioxide and nitric oxide get back again. So as this all these substances are in gaseous substrates, so this is called homogeneous catalysis. I think you can understand. In case of homogeneous catalysis, only intermediate compounds are formed. This is the intermediate compounds. But in case of heterogeneous catalysis, there will be intermediate compound, and also at first adsorption occur. Then intermediate compounds form, then products forms. But in case of homogeneous catalysis process, first intermediate substance is formed and then the reactant, then the products formed. So today we learned about the Arrhenius equation. We can solve exercise based on Arrhenius equation. We can know about the catalyst, different type of catalyst, and the analysis the mechanism of homogeneous and heterogeneous catalysis. So if you have any question, please write it in comment box. Later on, I will try to solve your questions. I have a home task for you. There are some questions. First one, a particular reaction has a rate constant of K equal to 2.3 into 10 to the power minus 3 at 20 degrees Celsius temperature and 4.3 into 10 to the power minus 2 at 90 degrees Celsius temperature. What is the activation energy of the reaction? How can a positive catalyst alter the reaction? What is the rule of catalyst Poisson in Rosenmund reaction? What are the key factors in heterogeneous catalysis? What is the role of promoters in Haber-Bosch process? What is the significance of autocatalysis? So thank you very much for your participation. I want to say you that again, you must stay at home and make your family member conscious about novel coronavirus COVID-19. You make your lesson properly and make the best use of your time. Wishing this, I like to conclude here. Thank you very much.